Okay, so this is the content for Chapter 9 of Callister, Part 2. And in this, we'd like to talk about microstructure and phase diagrams. So we have these phase diagrams, and they come from our understanding of the free energy curves and from thermodynamics. What do we know about the microstructure based on the phase diagrams? Well, strictly speaking, nothing. Strictly speaking, these phase diagrams are telling us about the free energy of different phases relative to each other as a function of composition and as a function of external parameters such as temperature and pressure. But they don't tell us about interfaces. They don't tell us about the size of grains. They don't tell us about the growth of grains. However, we can use these equilibrium phase diagrams, and that's an important equilibrium. We can use our equilibrium knowledge and combine it with what we know about kinetics and get an idea of what the microstructure will look like based on these equilibrium input. So let's start with the simple isomorphic alloy. So we've got constituent A, constituent B. Because it's isomorphic, they form a single phase alpha. And up here we have liquid, because this is phase diagram as a function of temperature. And we'll have some map that looks like this, which is our alpha plus liquid region of the phase diagram. So let's pick a particular composition, something in the middle here. This is again a function of fraction of mole fraction of B. If we pick this as some XB, I don't know, we'll call it star, right? This is a particular composition, and we mix A and B together and we heat it up until it's liquid. So we're up in this region. Well, if we look at the microstructure at this point, it's going to look something like this. We're looking at a little microscope, so we have a circle, I guess. It's all liquid. Okay, that makes sense. So now we take it and we cool it down until we just touch that phase boundary. And if we just touch that phase boundary, the structure looks like this. Mostly liquid, but then we also have a few embryonic nuclei of alpha that form. And the alpha is going to have composition let's call this T2, call this T1. So at T1, the composition of the liquid is just all XB star. XB star. At this point, we have a liquid, which is XB star, and we have alpha, which is XB, so I'll call this 2 because this is temperature 2. XB2. Okay? Now we're going to cool down a little bit further. At that point, so okay, we know that we're in the middle of a two-phase region. We draw our tie line. And our microstructure at this point now looks like this. Liquid. And now we have, that's about, if you look at the tie line, it's about 50% solid and about 50% liquid. So about 50% solid, 50% liquid, depending on how you eyeball that. This is going to be alpha. Now the composition has changed. So now the alpha has composition XB, I'm calling this temperature T3, XB3. Alpha is XB3, and the liquid is now defined here. XB3, we're going to call it 3L for 3 liquid. So that means L has composition XB3L. Okay? Keep cooling till right at that boundary again. And we're going to call this, so we draw our tie line. We draw, call this T4. The microstructure here is mostly alpha now, right? If you look at the tie line, it's 99% alpha and about 1% liquid. So our microstructure is going to look like this. So this is alpha. And we have some liquid between the grains. But it's mostly solid. The composition then is right here. So we have alpha, I'll call that XB4, which is really close to XB star, right? But not exactly there. So alpha XB4, and the liquid is going to have composition defined here, XB4L. So liquid XB4L. So it's fairly A-rich. And then finally, if we cool down further, so we're now in the alpha region of the phase diagram. That means that our microstructure now looks like all solid alpha. I guess I'm drawing alpha in purple, huh? No liquid. And the composition is given by XB star. So alpha XB star. And this is how we think about the microstructural evolution of a material using an equilibrium phase diagram. Now, talking a little bit more about microstructure, if we ask ourselves, how many nucleation sites are there, and how do these evolve? That's something that we can't tell from the phase diagram, but we do know that it's going to go through some type of ordering, such as this, right? The information about how many of these form and what their size is and what the equilibrium size is, that comes both from our knowledge of thermodynamics, and it comes from kinetics. If you remember from chapter 10, we talk about the nucleation, and the nucleation depends on the diffusion in the liquid. So that information we don't have, but we do know kind of qualitatively this is the structure, and we know if at any point in this phase diagram it's in equilibrium, this is what it should look like. So it's worth pointing out that we're assuming that these are coming and it's in equilibrium. And what I mean by that is that at any point we say that all the alpha has this composition. So we say that the kinetics are not at all limiting or controlling the structure and morphology. So this was the isomorphic alloy. We can also talk about binary phase diagram. We can talk about the binary phase diagram, or we can talk about even more advanced ones, but for the sake of this class and actually having a lecture which fits into this time period, we're going to just talk about the binary. So let's draw kind of a rough binary phase diagram. So this is temperature, this is mole fraction of B, that's A, that's B. We're going to have a binary phase diagram that has solid solutions. So we're going to have something like that. Alpha, go across, beta, this is liquid. So here we have alpha plus liquid, here we have beta plus liquid, and then here we have alpha plus beta. Touch there. Okay, so let's take first a simple path that starts out here. We're going to have something which is very close to the A side, or we pick the B side, but we're going to pick this composition. And we're going to heat it up until it's liquid. So we're up at that point. And at that point, we have a microstructure which is all liquid. And we're going to call this XB star. And that liquid has composition XB star. Cooling down. We're going to cool down until we're in the two-phase region, alpha plus liquid. And And in the two-phase region, we draw our tie line. Here and here. And the microstructure, if you look at this, with the inverse lever rule, we can say how much is alpha and how much is liquid. So if you call this A, I'll call this A, you call this A, call this length B, then the fraction of liquid is equal to, so the liquid's on that side, so it's going to be A divided by A plus B. So that looks roughly maybe 15% liquid. So drawing our microstructure here, we're going to draw around 85% solid and about 15% liquid. That's alpha, and liquid, the composition of the alpha is determined right here, which I'm going to call XB. I'm going to call this XB, let's call it 2, and call this temperature 2. So alpha XB2, and the liquid then is defined here. So that's XB2L, XB2L. Okay. So now let's keep, I'm going to zoom in here a little bit. So now let's continue cooling till we're in here. So now we're in the single phase region, it's all alpha, and that means we can draw our microstructure, and it looks like this. And it's all alpha. And the composition of alpha is given by XB star. Right? Because we're saying this is an equilibrium evolution, which means all of alpha has this composition. And in fact, it's going to have that throughout this single phase region along this line. Now let's cool down further. We're now going to cross that boundary, and we're going to come into this two-phase region. Well, the two-phase region, that's going to be temperature. Let's see, I called this T3, so let's call this T4. We draw our tie line, and we draw the tie line in the two-phase region. And our microstructure at this point, it looks like this. It's mostly alpha. Well, we can figure out the amount here by looking at the tie line, right? So let's define this little part to be P, and then we define this length to be Q. So the fraction of alpha, which is on this side, is going to be Q divided by P plus Q, the length of the tie line. And that looks like, it must be around 98% alpha. And then that means it's about 2% beta. And the microstructure then is going to look like this. That. This is alpha phase. And then interdispersed, we're going to have little parts of beta that are interdispersed in the alpha phase. And if we want to look at the composition of the beta is going to come from drawing a line down. That's going to be XB for beta. So beta is going to be XB for beta. And then the composition of the alpha, draw over here and draw down, well, kind of right there, which I hope you can see. That's around what I'm labeling as XB4. So then the alpha phase is XB4. So this is the microstructural evolution in a binary eutectic when you're cooling outside of the eutectic region, so you're cooling through the single phase region. And again, the exact morphologies and grain size and nucleation distribution, we can't get that from the phase diagram, but qualitatively we know how it should look, and we know what the compositions and the phase fractions should be, assuming an equilibrium distribution. But there's other regions in this phase diagram that we can also look at. So let's draw another one of these. B. So liquid alpha plus liquid alpha, alpha plus beta, beta, beta plus liquid. Okay, so this is our eutectic point, and we know that this eutectic line, anywhere along this line, you have three phases that are coexist. Let's pick a composition which puts us right at that eutectic point. XBE for eutectic. Okay, so we're going to be in this, we're going to heat it up until it goes into the liquid region. In the liquid region, we have a microstructure, which is again all liquid, and the composition is given by the total composition of the system. We cool it down until we just cross into the two-phase region, right? So we form a solid, and in fact we form all solid. This entire liquid region transforms into an alpha plus beta. Well, this eutectic region is kind of special. It allows for the development of a microstructure that we call a eutectic microstructure. And the eutectic microstructure is going to look like this. it has these plate-like structures. And what this really is, if we zoom in, zoom in here, is we have layers of alpha separated by beta. And it doesn't always have to be stacked plates. You can also have little rod-like structures of alpha that are going through a beta matrix. But regardless, it's an alternating structure. And this alternating structure is going to give us a segregation of the composition. And what I mean by that is that if we go to this, our point, and we draw our tie line, well, in this case, let's define this distance here as P, this distance as Q, then the fraction of alpha in our microstructure is going to be, well, alpha's on that side, so it must be Q divided by P plus Q, and the fraction of beta on that side, so it's going to be P divided by P plus Q. And looking at this, that's around it's around a 1-to-1 ratio, huh? Okay, what about the composition? Well, the composition of the beta we can determine by going over and then drawing a line down. So this is going to be XB beta, and the composition of the alpha is determined by drawing over to where we touch the phase boundary and draw a line down, XB alpha. So what this means is it means that the alpha phase is very A-rich, right? It looks like it's maybe 15% B and about 85% A. On the beta side, we have exactly the opposite, right? It looks like maybe it is 90% B and 10% A. So what happens is, as you cool through this eutectic point and you make a eutectic microstructure, you're getting segregation of the A and the B atoms into layers. So this alpha is A-rich and the beta is B-rich. And that means that the process of forming this is very, very diffusion intensive, right? Because you're basically you're separating out A and B atoms from one another. Now, we know the composition of the alpha, and we know the fraction of alpha. We know the composition of the beta, and we know the fraction of the beta. And that can tell us the total composition of the system, but we also know the total composition of the system is right here. So you guys can do this at home, and in fact I encourage you to do that because you'll learn a lot. You'll find that the combining phase fraction and composition of alpha and beta will give you exactly the total composition, which agrees exactly with your eutectic composition, or the composition that we put in originally. So that's another transformation path that can occur in a binary eutectic system. And let's look at one final possibility for what can happen in a binary eutectic system. liquid alpha beta, alpha plus liquid, alpha plus beta, beta plus liquid. X, B, T. Okay. So let's pick a system that has composition around here. X, B, star. Okay, we'll take that and we're going to heat it up until it melts. And then that means we have a microstructure, which is all liquid and has composition X, B, star by definition. We're going to cool this down until we're in the two-phase region. I'm going to call this T2. We draw our tie line, and from our tie line we can determine how much of alpha and how much of liquid is present. So if we call this P, we call this Q, then the fraction of alpha is, there's alpha on that side, so it's Q divided by P plus Q, then the fraction of liquid. The liquid's on that side, so it's P divided by P plus Q. And roughly, that looks like it's around 30%, and this is around then 70% liquid. So our microstructure is going to look like this. Alpha, 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 and the composition of alpha comes from drawing our line down where the tie line intersects the line here. So that's going to be X, B, 2, and this liquid is going to be X, B, 2L. So alpha, X, B, 2, and liquid X, B, 2L. Okay. Now let's keep cooling, and we're going to cool it down till it's just above that line. So it's just above the point where it transforms into the eutectic composition, or sorry, not eutectic composition, but the two-phase region. And we're going to call this T3. We draw our tie line, and defining our P and Q at temperature T3, we get, well, it's the same, right? But looking at it, the fraction of alpha is around maybe, what, 1/3, so maybe 66%, and the fraction of liquid is around 33%. Well, 34, why not? 34%. And the composition can be determined by looking where the tie line crosses the boundary, coming down, calling this X, B, 3. That is X, B, 3L. So the microstructure at this point is going to look like around 2/3 alpha, So that's going to be alpha, 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 alpha. And alpha has composition XB2. The liquid has composition XB2L here. Okay. So now the next step is we cool it, and we're going to cool it just into the two-phase region, or the two-phase solid-solid region. Okay, so what just happened there was we went from having in a single, change. I mean, this is, if you want to imagine it, change the temperature by 1 degree. Well, we drop it 1 degree, and we have had about 34% liquid. Well, that 34% liquid instantaneously transforms into alpha plus beta. And kind of skip to the punchline here, what that means for the microstructure. So the microstructure now looks like, I'm going to try to mimic that microstructure as best I can. Here we've got alpha, 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 alpha. And now in this region we have a two-phase eutectic microstructure that fills in here. And in that eutectic microstructure, we have beta and then we have alpha. The alpha that's sitting in these large grains is called primary alpha. The alpha that's in the eutectic microstructure is called eutectic alpha. So we can distinguish between the two if we want. When we talk about thermodynamics, we talk about constituents, and we talk about A and B, which in this case could be tin lead or something else that forms this type of binary. But we can also talk about micro-constituents, and that would be subsets of the microstructure, and we can talk about the eutectic phase being a microconstituent of this microstructure. Microconstituent. Okay? So we got kind of a picture of what's happening. Quantifiably, what do we know? Well, quantifiably, we know that this is, let's get a different color, that this is our global composition, and we know that the global composition of this microstructure is going to be XB star, but we also know that the alpha and the beta will have different compositions, and we know there's a different amount of fraction of each. So let's draw a tie line that goes across, if we define this to be P, and define this to be Q going across there, then the fraction of alpha, so alpha's on that side, so the fraction of alpha must be Q, right, because it's the opposite of where it is, or of where the tie line touches the alpha phase, over P plus Q, and we know the fraction of beta then is P divided by P plus Q. Then, so that is really telling us then that it looks as though alpha is what, 90% maybe? At 10%. If we had numbers here, we could calculate it, but just roughly, we've got about a 90% to 10%. And then talking about the composition of the beta is going to be X, and I'm going to call this T4, so XB4 beta. That's composition of beta into here. And then the composition of the alpha is where the tie line touches that phase boundary, and that is XB4 alpha, which gives us the composition here. And because we are saying that our system is in equilibrium, that tells us that all of the alpha in this phase has the same composition, which is XB alpha 4. All of the beta has composition XB4 beta, and the net is going to be defined by our composition, which is XB star. So this is what can happen, and of course the same type of interactions happen over on the other side of the phase diagram. This is what happens when we talk about phase evolution in equilibrium. We can also talk about a non-equilibrium microstructural evolution if we combine our knowledge of equilibrium thermodynamics with kinetics from what we know about diffusion. So let's look at an isomorphic alloy as an example. Okay. That. Got liquid, alpha, alpha plus liquid. And let's say that we pick composition here at XB star. Okay, so we're in liquid. We know the composition. If we then cool down to the point we just cross and start forming a solid, we can draw our tie line like this, and we know the composition of the solid that forms, and that is going to be here, XB1 alpha, because we're going to call this temperature T1. And the composition of the liquid then is here, XB1L. So at this point, the microstructure is going to look like this, and we have a little bit of alpha, looks like about 10%. FL percent. That's kind of like this. Okay, so now if we take and we cool this further down to here, we can determine the composition of the solid that precipitates out of the liquid by drawing our tie line. And the solid coming out is XB2 alpha. This is temperature T2. But we are saying this is not in equilibrium. We're going to talk about kinetics and how they impact the structure. So when we precipitate this new solid, that forms on the outside of the existing solid. And because diffusion in a solid is relatively slow, well, especially compared to in a liquid, we know that what's going to be coming out is actually going to form on the outside of those existing grains. So, and it's going to have composition XB2 alpha, and the liquid region have composition XB2 liquid. But if we talk about the net composition here, right? We originally had XB2 alpha, and then we had XB1 alpha, and then XB2 alpha. There's actually extra B compound because of these little yellow crystals in the center. So effectively, we have a solid which is actually over here. So the phase fraction is going to be defined by drawing the lever rule from here to here, just outside of the two-phase region boundary. So it acts as though there is a shift of this boundary kind of off from it. So let's keep looking at the evolution, and we'll see how this works. So we'll cool this a little bit further. At this point, the composition of the solid that's forming is XB3 alpha, because it's T3. And that, again, is going to form on the outside of these existing crystals. And again, this is poorer, or has less B in it than the original, but the interior of the crystal has too much, and because we don't it has too much to be in equilibrium. But because we don't allow for diffusion, that means that our effective solid has a composition which is going to be out here. Which means that talking the phase fraction can be determined by applying the lever rule, where this is P, this is Q. So at T3, F of alpha is equal to, so that's alpha over there, so it's going to be P over P plus Q, and F liquid is equal to Q over P plus Q. Now the thing is, because we're pushing this phase boundary further to the right, what we're essentially doing is we're saying that there's less volume, or less total fraction of phase that forms. or volume fraction of phase that forms relative to the liquid, but it's richer in B because the interior has excess of B atoms. And what we're going to find is that all along here, as we cool, we're going to keep adding a phase that is less rich than the interior. Let's get another color here. Until we reach, and in doing that, we are again essentially extending this phase boundary over to the right. And what this means is it means that when we reach where the original equilibrium boundary is, and crossing the temperature below that should result in the removal of the liquid, well, we still have liquid. And in fact, we can proceed down here and still have a portion of liquid. Right? At this temperature, it looks like it's around 20% liquid still. And that proceeds until this effective boundary is crossed. And at the end of the game, when we reach that point, we have a microstructure that is solid. I'll put the phase boundaries here. These are, but the interior and the very center has composition of the first solid formed, which is XB1 alpha, and then it gets progressively more dilute of the beta, or sorry, the B composition, until you wind up out here, and the final composition at the exterior of the grain, or near the grain boundary, is going to be XB star. So we get this gradient and it goes from the interior to the exterior of the grains. The exact nature of the gradient and the degree to which we extend the phase boundary, that depends on the individual crystal, and it depends on the diffusion, it depends on the temperature. So, telling you exactly what those should be is hard without having some experimental determination, but we do know that there is going to be this composition gradient. And this is sometimes called coring of a crystal, meaning that it has a concentration gradient from the center to the exterior. And this is an example of how we use an equilibrium phase diagram to predict the non-equilibrium behavior. And if you get a book such as the textbook by Porter and Easterling called Phase Transformations in Metals and Alloys, that entire book talks about the phase evolution of a material in non-equilibrium conditions based on the equilibrium phase diagram.